Okay, so let's do chapter 9, exercise problems. And here we have the problem 9.2.1. I'm sorry, I have a dog and he has a play date. So both of them are kind of making these noises. So just bear with me. So anyway, so here we have this problem 9.2.1. This is the exercise problem. And here we need to find the wavelength. We are given the frequency and we are given the speed of light. So the formula that is going to be used is, we know that C is equal to, so I need the space. So so this is known, C is equal to lambda nu. Rearranging this, because we need to find the wavelength. So wavelength is equal to the speed of light, C, over the frequency. Okay. So this is lambda, L, A, M, B, D, A. And this is called nu, Greek symbol, nu, N, E, U. So this is frequency, and this piece is the wavelength, of course. Now, you guys are well aware that the center of the atom is the nucleus, which contains the protons and the neutrons, and all around are the energy levels. These energy levels have a certain value. The closer they are to the nucleus, the less their energy is. And as these energy levels go further away from the nucleus, the magnitude of the energy increases because the nuclear pull decreases. So here we have these electrons in these energy levels, and these electrons can jump from a lower energy level to a higher energy level, or from a higher energy level to a lower energy level. So when they jump from high, this is the low, so this is the energy level 1, energy level 2, and energy level 3. So when they jump from high, this is high to low, or from low to high, they emit light. And this light, as we know, has colors, right? So we used our spectrum, our visible spectrum. We knew all the 7 colors of light: violet, indigo, blue, green, yellow, orange, and red, right? So each of these colors have some energy associated with them. And this energy, we had done several experiments. So whenever these electrons jump, the color of the light matches with the wavelength and the frequency. Okay, so the wavelength, using what wavelength, that is, we can determine the color of the light, the color of the light, and then we can measure the energy of these energy levels. So that's how these energy levels got their values. Now, there is also, when the light colors, these colors of the light, as we said, they have energy. So based on that, the spectrum, there is the emission spectrum, EMMISSION, or I don't know, EMISSION, and the other is the absorption spectrum, EBSORP, absorption, TION. Okay, so emission is when they go from top to bottom, higher to low, right? From let's say from energy level 3 to energy level 1. And absorption is when they move from low to high, from energy level 2 to energy level 6, like that. From lower to higher, absorbing, and higher to low is emission. So anyways, these spectra for metals, they have they are basically the fingerprints of of every element. Every element that you see in the periodic table has very specific energy level and energy levels, and these relate to their spectrum. Now, there are 2 types, just, the rainbow, right? Rainbow is a spectra. So similarly, for the metals, there is line spectrum. So the colored lines, so if you see them through a spectrometer, you will see that these lines, colored lines at a certain distance, at a certain wavelength, these colored lines, these relate to the energy levels. So there are labs, which in other classes, you will do in higher level classes, but for now, just, this is sufficient to know. Now, let's do the calculation. So wavelength is equal to the speed of light is 3.0 into 10 to the power 8 meters per second over the frequency, which is 1.55 into 10 to the power 10. Okay, and that is seconds inverse. So seconds inverse is meters. So basically, seconds inverse also means per second. So, so you can also write this meters per second as meters seconds inverse. And here also is seconds inverse, right? So here the seconds inverse and second inverse will cancel out. Okay, so now the rest is just doing the math, which is 3. So the way I'll do this is 3.0 divided by 1.55. Okay, and then times 10 to the power 8 multiply by 10 to the power minus 10. Now, if you have a scientific calculator, you can do it. But if you don't have a scientific calculator, then you can just simply, if you don't have a scientific calculator, then you can do it manually as I'm showing you. So here we have 3 divided by 1.55. And here you have 1.93 into 10 to the power minus 2. Okay, so that's the wavelength, and that is going to be in meters. So one example is one way you can write this answer, or another way is that you can move the decimal. If they wanted like a complete number, then you can move the decimal and you can get it as the other number. The other answer would be 0.0193 meters. Yeah, that's generally, wavelengths are in meters. So that's what it is. So 10 to the power -2 means that 100. So means divide by 1,000. You could divide by 100, sorry. So then that will give you this. So this also means, I'm just doing a little math here. So this would also means 1.93 divided by 100. And that gives you back this answer. Okay, so this is just to show you how to do this, but this is how you will solve this problem. Okay, next is we are looking at the electronic configuration. Now I want to do a little bit of the theory on this electronic configuration. So what is this? So we talked about earlier that the energy levels exist, right, in the atoms, and each of these energy levels contain electrons. Now, we know that these energy levels are equate the energy level to a city, right? Energy levels are made up of subshells, just like the cities are made up of streets, right? Every street have some living arrangement, like apartments or mansions or houses or single family homes, apartments, 1-bedroom apartment, those things. Okay, so we have these what are these called? These streets containing these houses or the apartments. And then the apartments can, especially the apartments or the condominiums, you can only house so many people. So if there are 1-bedroom house, 2 people, 2-bedroom house, so 4 people can live. So like that. Okay. So consider it to be like this. So we are trying to place the electrons in the energy levels. Okay. Where are we placing them? Outside of the nucleus. Very specifically, so every energy level can hold a certain number of electrons. So energy level 1, which is very close to the nucleus, has a small energy level and it is very strong nuclear pull. Energy level 2 is further away from the nucleus. So what is going to happen? A little bit of the nuclear pull becomes weak, right? Because a shielding effect is also occurring, because now you have energy level 1, blocking the view of the nucleus on the energy level 2. Now, energy level 3 is even far away. This is 3, actually. This is 3. So energy level 3 is even further away. So when it's further away, now energy level 1 and 2 are blocking the view of the nucleus on the last energy level, which is 3 in this case, as I've drawn. Now, what happens is that the electrons that are further away from the nucleus have more freedom. They can easily leave the atom if if they are able to, if let's say they get some more energy. So what happens now that these electrons, if they leave, then if they can leave, then they can form charged particles, right? So we will talk about the charges later, but right now, focus on that if we were to place the electrons, so first thing is, you can only place that many electrons in the energy levels as there are the number of protons. Remember, for the neutral atoms, protons and electrons, they are the same. So if you have to place one electron, one proton, if there is one proton, then only one electron needs to be placed in an atom. If there are 5 protons, only 5 electrons need to be placed. If there are 10 protons, then only 10 electrons need to be placed. But where should they be placed and how? So there is a electronic configuration. This is a pattern. This is a rule. Okay. This is the rule. I have it wrong. Give me a break. 1 minute here. Let me just check on it. Okay. So you see, like, okay, so there is a certain order or certain pattern. This filling of the electrons has to occur. So we see that every energy level has a certain capacity to keep electrons or to hold electrons. So energy level one can only hold 2 electrons. Okay, so here's the energy level 1, because it has only one subshell. It has got only one orbital, and the name of the orbital is 1s, and maximum of 2 electrons can go in each orbital. Right, so one orbital, regardless where it is, every orbital can only hold 2 electrons maximum. So we have these 2 electrons. So if you have to place 2 electrons, they're first going to go in the first energy level, first subshell, first orbital. The name of the orbital is s, and then those 2 electrons go there. Next is the next energy level is the second one. The second one is a bigger energy level, so it has got 2s and 2p. These are the 2 subshells. So the name of the subshells and the name of the orbitals match. So 2s subshell and 2p subshell, right? And 2s, so these are the orbitals also. So basically, where is the probability of finding the electrons? It's maximum in the probability of finding the electrons is always in the orbitals. So we are now, from now onwards, I'm just going to use the word orbitals. So the remaining electrons are going to, so if you have, let us say, for example, you have 10 electrons, okay, to place. So the 2 electrons are going to go first to the 2s. Next 2 electrons are going to go to the second energy level, second subshell, and the second 2s orbital. The remaining 6 go to the next one, which is in the same energy level, but in the 2p orbitals. And in the 2p orbitals, all 6 of them are going to station them. So you have to look at the videos with more bigger lecture on orbitals and filling of the orbitals, their shapes, and all those things. But here we are going to just cover up the basic information that you need to solve the problems that relate to the electronic configuration and so forth. So anyway, so next comes the third energy level. So if you have more electrons, let's say if you have to place like more electrons, then they are going to go to then you're going to place them in the third energy level. So 3, and then third shell, and then third subshell. Sorry about that. Okay, so those who have dogs can understand. Anyways, so sorry for a little interruption here, but anyways, let's look at this. So the remaining, so let us say you have like a large number of electrons, a lot of electrons. So this is how the filling is going to occur. The order of filling is, then they first always fill the first 1s2, 2s2, then 2p6, then 3s2, then 3p6. Now after 3p6, it's not very linear. After 3p6, you will see that the electrons, they kind of like the energy levels, they overlap. And so the filling of the electrons, it's not in that linear order. So after 3p comes the 3d. After 3p comes 4s2. Okay. And after 4s2, we would expect 4p6, and we would expect 4d, right? and 4f14, but that's not the case. What is coming after that? What is coming after 3D is after 4s2 is 3D. Okay, now keep this in mind that first energy level, only one subshell. Second energy level, two subshells. Third energy level, three subshells. Which ones are those? 3s2, 3p, and 3d. Fourth energy level has four subshells, 4s2, 4p, 4s, 4p, 4d, and 4f. Fifth energy level has five subshells. Let me get a different color. Okay, so 5s, 5p, 5d, and then 5f also. Okay, and so this is like a different, like bigger. Next is the 6s. Same as the case, 6s and 6p, and then all these, and then comes the 7s. So these are like very big energy levels. And the atoms that we have about 117 atoms. So the naturally occurring ones are stable also, but the bigger the atom gets, the bigger the nucleus becomes, so it becomes unstable also. So, but up till now for our course, we are looking, this is an introductory course, so we are going to just look at the, up till the D and then a little bit of the F. So, but anyways, let's look at the placement. Here's your periodic table, okay? Now, you see these numbers right here. Let me use this color. So 1, 2, 3, 4, 5, 6, 7. What are these? These represent the energy levels. These represent the energy levels, okay, or the shells. So energy levels. Okay, so what are the energy levels? These are the energy levels. 1, 2, this is 2, this is like together. Second energy level, this is the first energy level. So the number in front is the energy levels. So that's what it is. Okay. Then what is the next thing? What are these? What are these? These are columns. And these, what do the columns represent? The columns represents the valence shell. Okay. So these are, again, let's just point this here. So these are energy levels all the way from here to here. Okay. The top ones here, all these are the valence. These represents the valence shell. Now, what are valence electrons basically? Valence electrons. What are valence electrons? Valence electrons are the electrons that are present in the last shell, the last orbital, the last shell, sorry, not the orbital, but the last shell. Okay. All right. Now, so these are the last electrons. So last, like the shell number in the last shell or the energy level. Okay, so energy levels, and I'm also going to put here shells because that is also used. Okay, now we see that this is besides that, there's also, keep this in mind, that 1 stands for these columns. These columns also represent how many bonds they can make. So they can make, like if you were to put this bonds, so elements that are in group 1A will make 1 bond, 2A will make 2 bonds, 3A will make 3 bonds, 4A makes 4 bonds, right? 5A will make 3 bonds, 6A will make 2 bonds, 7A makes 1 bond, 8A does not make any bonds, right? So here is the valence shell, valence electrons. These are basically the group numbers. So the group numbers, and these are also called rows. Okay, these rows represent the energy levels. So the group numbers, these are the main ones. These are the group A. But the bottom one, the middle ones, these are the group B, the center ones from here and here, this would account as B, right? So I have to write other things also. So anyways, now we are looking at the blocks. What are the blocks? So pay attention to this one. This whole piece and these two. Now, keep this in mind. There's another thing, that S has 2 orbitals S has 2 orbitals. So it can hold a maximum of 2 electrons. P has 3 orbitals. S is only 1 orbital. S is only 1 orbital and it will hold 2 electrons. P has 3 orbitals and it can hold a maximum of 6 electrons, right? D has 5 orbitals and it can hold a maximum of 10 electrons. And F has 7 orbitals, so it can hold a maximum of 14 electrons. Okay, now this is the S block. S block. Okay, so here we are putting the blocks. The red ones are the blocks. So S block, S can hold a maximum of 2 electrons. So all the atoms that have only 1 electron in the last shell, in the S1 electron, are going to go in group 1. Those atoms that have 2 electrons in the last shell, and that is the S orbital, 2 electrons in the S orbital, and that's the last, they're going to go in the second column. So that's the S block. So there, in other words, the valence electrons, when they fall in, if S1, the last electron, the valence electrons, if they go in S1, then first column. If it's S2, then it's the second column. All right, so watch the YouTube videos watch my videos on full lecture. So I've explained more details there. So anyways, right now, I'm hoping, because this is just a review, so I'm hoping that you already know it. So let's look at now the other one right here. P can, so look at this. So S, so let me color this one back again. So here is the S1, or S has 1 orbital, but 2 electrons can be held, right? So therefore 2 columns. So these match with the columns. These columns, let me put here. These match with the columns. These numbers match with the columns. So S can hold 2 electrons, so 2 columns. But now think about it. P can hold a maximum of how many electrons? 6. So how many columns do we see on this side? These are all P blocks. 1, 2, 3, 4, 5, and 6. Okay, 6. And here we have the P block. P block. So 6 electrons. So if the last electron ends in P1, so it is in the first column in the P block. If it ends in the, so this is the first column. So so you get that. So this is the first column in P block. Okay. So same is the case here also. This is the first column in S block. Okay, now we have similarly the second column. This is the second column. So this is the first, this is the second, this is the third, this is the fourth, this is the fifth, and this is the sixth column. But you know, this is the helium is different. So here, sixth right here. Okay. Same story with the D block. Now D block, D is what? D has got 10 electrons, right? So let's change this color here. So this is the 6 electrons here on the P block. Now look at the D block, which is the D block, 10 electrons, D. So this is first D, this is the electron that is going to be ending. The last electron is going to go in the D block. The last electron is going to go in the D orbital. But if it's only 1 electron that goes in the D orbital, then it's going to be placed here in D1. 2 electrons in D, D2. 3 electrons in D, D3. So in other words, all these elements that I'm putting in these columns will all end in D1 in the first column, D2 in the second column in the D block, D3 in the third column in D block, fourth column in D block means D4, fifth column in D block, all of them will have D5. Sixth column will D6, seventh column D7, 8, 9, and 10, all of them. Okay, so D block has got these 10 columns, and each represents the placement of electrons in that orbital. And same, now you can imagine that the F block, and F block is what? How many can F hold? F can hold a maximum of 14. Oh God, sorry. F can hold a maximum of 14. So we have here 14 electrons, and that is the F block. So 14 electrons. So this is going to be F1, F2, F3, F4, F5, F6, F7, F8, F9, F10, F11, F12, F13, and F14. So all the elements that are in that column will all lanthanides and actinides. So F1, F2, F3, F4. Okay. So that is this one is the F block. Okay, so the last electron, where is it placed? So that placement is important. So when we talk about the placement, we talk about where is that present? Is this present in the, where is it present? So we have to look at the group number. The group number identifies the valence electrons, which are the last electron. Then comes the period number. Period number represents the energy level. Then we look at the blocks. Okay, in the blocks, whether it is S, P, D, or F. So which valence electron is going to be in which orbital, and so, and then we're going to look at the column in the block. The column in the block is the absolute last electron. Okay, so now let's look at some of the examples here. Okay, so here we are given magnesium. Okay, magnesium. Now you look in the periodic table and you identify. Now there's something you're going to do from your side also. And let me see if I can open up the periodic table. So give me a minute. All right, so here is the periodic table. Okay, so we are talking about magnesium. So magnesium is here. All right, so where is magnesium? Magnesium is present in the S block, right? Second column on the S block. So second column on the X block, that's a group number, and it is present in the third row. So let's do third period. So let's write this down. Magnesium is present in the second column in S block. So this is, in other words, the question that the students ask is, where do you stop? When you look at this, where do you stop? You know, so of course you stop based on, you know, the number of electrons that you need to place, but let's look at, we need to place them correctly also. So the last placement. So second column in the S block, and what row is that? The third row, So what does it go to? The absolute last electron is going to look like, so third row, so 3, S, and 2. Okay, so this is what it means. The third row, 3 is this number, S is this S block, the block part. Okay, and because it's in the second column, so it's the 2. Okay, so the rest is, okay, those students, you know, after some time you begin to memorize this, but let us say you forget, you can always consult the periodic table. So once one thing is there, we need to stop at 3s2. Let us say we need to stop here. This is where we're going to stop. Okay, 3s2, where I made that dot. Okay, so what are you going to do? Fill in 1s2. So this 1 can hold a maximum of 2 electrons. So 1s2 is going to be filled up. Then comes the 2s. So fill up the 2s, then 2p. Fill up the 2p. All of the 2p's become like maxed out at 6. So 2p6. And then left over, go to 3s1. So let's look at it this way. 1s2. So we have, sorry, one thing. We need to identify in magnesium how many electrons there are. So magnesium has this number, magnesium 12 and magnesium 24. So which one will you use? Magnesium 24 or magnesium 12? Remember, this is the atomic number. This atomic number and this one is the mass number. So we are not going to touch the mass number here. Mass number don't. Atomic number, this represents the number of electrons. Okay, this is the, so we are going to place, we need to place 12 electrons. So out of these 12 electrons, 2 electrons go to 1s2, the remaining go to 2s, fill that one up, and then the leftover go to 2p6. So we have accounted for 10 electrons, right? And then comes the remaining 3s and 2. So 12 electrons. So you count these. So you can count this also. 2 plus 2, 4 plus 6, 10 plus 2, 12. So all the 12 electrons get accounted for. And where it's placed, it's exactly placed where, you know, it stops exactly where it's supposed to be. This is the placement in the periodic table. All right. So this is the way we place them. Now I'm going to do more electronic configuration, but let's look at these two guys first. 9.7.1, predict the placement. Okay, so here we are looking at titanium and chlorine. So titanium is, where is titanium? Titanium is in titanium. So we are just looking at the placement. They're not asking us to do the electronic configuration in these questions. So titanium, if you look at, here is the titanium right here. Okay, so where is it placed? So if you look at it, this is placed in the D block, right? In the D block, but it is placed in the second column. Now comes the question. Is it the fourth row? Is it the fourth? No. Remember that. Right where scandium is, right where 21 is written, right there is a start of 3D. So all this periodic table is rows is fine, but something I should put here is that 3D. This is, I had this, I forgot. So mark this. This is the start. This is 3D. So this row is fourth, but that's the 3D. The start is here. This one is 4D. So the Ds are like, you know, one row behind. 4D. Okay. And then 5D and 6D. And then these are the F blocks. So these are these come from here. The F blocks gets transitioned out. So so they are placed, otherwise the periodic table will extend too much. So and F blocks are basically, they are rare earths. They're not, you know, very common. So now let's look at, so titanium is over here where I made this round circle. Okay. So it is going to be in 3D, but it is in the second column. So it is D2. Okay. So let's do this. So this is placed. So the answer to this is 3D2. Okay, so this is going to be where the absolute last electron is going to go. Okay, so let's do the electronic configuration now. So 1s2, 2s2, 2p6, 3s2, right? And 3p6. Remember that after 3p6 comes on. So like I'm saying, 1s2, fill in the first what is it called, the box. Okay, one, and then this one also, the helium, actually this is helium. So we have placed helium and hydrogen, like some places you will see they are placed side by side, but we place helium with the noble gases. So but it is 1s2. That's for the helium. Okay, so helium and hydrogen. There, that's there. It's 1s2. 1s2 is for hydrogen, and 1s2 is 1s1 is hydrogen, and 1s2 is helium. Okay. Next comes the second. So this is going to fill the 2s2. Okay. Next is you max out on the p's. So here you take the 2p, and if you just have, or you still have leftover electrons, fill in 2p6. Right. Any leftover electron goes to 3s. So then you fill in 3s2, right? So if 3s2, you have still leftover electrons, then you go to 3p. Fill in the 3p. All of this is 3p. The second row, the second one. The second one here, but it's actually third row. Okay, let's say you have many leftover electrons, then you go to 4s. After 4s comes 3d. And then you fill in all of the 3D, and then comes the 4p. So this is all 4p starts from here. This is 4p, and this is the 3D, and this is the 4s. Okay, so Again, this would be 4s2, that would be 4p1, 4p2, 4p3, 4p4, 4p5, 40, and then all the way till 4, and then comes the 5s. And then after 5s is 40. So one way is you can look at the periodic table and do it, or if it's easy for you, you can just put it in this linear fashion. And I know students like the linear one, so that also can work for you. Okay, so whatever worked for you, you can do it that way. Okay, anyways, so now we have titanium. So let's do this titanium right here. So 1s2, 2s2, 2p6, 3s2, 3p6, then comes 4s2, and then 3d2. Okay, because after 4s is 3d, but 3d can hold a maximum of 10. But if we only have 2, then we don't need to. Okay, so we just put 2. So now let's count 2. Oh, wait one sec. I always forget that. I'm sorry about this. This is one thing, but titanium is 22. Titanium is 22 electrons. Okay, so these 22 electrons are 2 plus 2, 4 plus 6, 10 plus 2, 12 plus 6, 18 plus 2, 20 plus 2, 22. So all the electrons got accounted for. Now, I also want to do one thing here before, we I don't know if that's not covered in this book, but that's the thing, certain things were missing. So anyways, we are going to look at, so this is the normal ground state configuration. This is the normal ground state. The ordinary is a normal one. Okay, now we are going to look at the condensed version, the condensed state. Okay, so ground state configuration is this. The condensed, or this is also called a noble gas configuration. Condensed or noble gas configuration. Now, what is that noble gas configuration? Noble gas configuration is where we are bringing in the inner core looks like the nearest noble gas. So which one is that? The nearest noble gas is going to be, in this case, let me put this here, the nearest noble gas is one row above, or one period above. One period above. Okay. Okay, so we have 2 plus 2, 4 plus 6, 10 plus 2, 12 plus 6, 18. So all these 18 electron match with the nearest noble gas, and that one is argon. Okay, so argon, so we are going to put this argon, all 18 electrons have the electronic configuration similar to argon, and the leftover is 4s2 and 3d2. Okay, 4s2 and 3d2. So here we see one thing, that no matter how we place them, don't worry about the placement, but it's always the highest shell number, or highest shell number. The highest shell number is 4. So this is the valence electrons. Valence electrons. So the valence electrons, the 2 valence electrons, highest shell number is the valence, always the valence electrons. Okay, so keep that in mind. So although we write D after 4s2, but it's always the highest shell number. So don't forget that this is the valence shell. This is a valence shell. The 4th shell. Okay, or the 4th, like the fourth energy level. Okay, so I'm just going to do this because this one was just asking about a placement, so you get an idea. Okay, all right, I want to do one more here. This question is not, so let's do B, let's do of, let's say, lead. Okay, lead. And we're going to write down both the condensed and so lead. How many electrons does lead have? Lead has got 82 electrons. 82 electrons. Okay, 82. And where is lead placed? Lead is placed. Let's look at lead. Sorry, lead is, where is lead? Lead is placed here, PB, right here, 82. Okay, so where is it placed? It's on the P block. In the P block, it is in the second row, second column. So obviously, its ending is going to be in P2, second column, P block, P2. Now, we see that this is in the sixth. Now here, this is the sixth row, sixth period. So this is going to end in 6P2. Okay, so always best to keep it so you don't forget. Sorry. So 6. So the placement is 6P2. Okay, so let's do this now. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3p6, no, 4s2, then 3d10. Okay, then 3d10, then 4p6, then 5s2. Okay, after 5s2, just to make sure that you are getting this, after 5s2 is 4d10. So here, after 5s2, so this is the after style, I made a mark here, 4d10. Okay, so 5s2, 4d10. After 4d10 is 5p6. Okay, 4d10, 5p6. Then 6s2, 4f14. Then 5p6, then 6s2, 4f14. And after 4f14 is 5d10 and 6p. Then 5d10, where did I write? Okay, 5d10 and 6p2. All right, now focus this thing. Let's add these numbers just so we get 82. Okay, so here 2 plus 2, 10 plus 6, no, 2 plus 2, 4 plus 6, 10 plus 2, 12 plus 6, 18 plus 2, 20 plus 10, 30 plus 6, 36 plus 2, 36 plus 2 is 38 plus 10, 48. 48 plus 10, 48. 48 plus 10 is 58. Did I get this right? 1 minute. I may have lost it. My dog is still barking. So here we have 10, 18, 20, 30, 38 plus 10, 48. 48, 48, 48, 54, 55, 56. 56 plus 56. 1 minute. 5, I might have to just stop here. 54, xenon. Xenon is 54. Okay, so we're going to stop at 5p6. Yeah, so all this is the condensed version. So all these 82 electrons, but till this part, we have 54 electrons. Okay, and these 54 electrons look like the nearest noble gas, which is xenon. Xenon, which is one period above. So xenon, 54, and then the remaining 54, 55, 56, 56 plus 14 is 70, 56 plus 4, 70 plus 10 is 80 plus 2, 82. Okay, so the remaining I've checked them. So these are all good. All right, so all accounted for. So xenon is 54, and now the leftover, you're going to just write down as it is, which is 6s2. Then 4f14. You don't have to, like, it's all only the nearest noble gas, no other. So 6s2, 4f14, 5d10, and then 6p2. Okay, so leftover electrons, you put them like that. Now comes, which is the valence shell. The valence is this, largest shell number, 6s2 and 6p. Okay, so the largest shell number is 6s2 and 6p. All right, so 6s2 and 6p2 are the valence electrons, valence shell, and these are the valence electrons. So 4 valence electrons total. Valence electrons are not p2. All right, the valence electrons are in the largest shell number, so don't forget that. So here you have the 4 valence electrons in lead, and in magnesium you have 3s2. So 3, the largest shell number is this, 3, largest shell number. So let me put this here. This is the largest shell number. So that is the valence shell. Okay, no matter how you place them, but it's always the largest one. And you have to combine all the large. Remember that these energy levels are made up of SVD, subshells and orbitals. Okay, so we did the placement. Now we are going to look at the trends in the periodic table. Now, trends in the periodic table, you guys have your handout, and in the handout, I have given you these trends. So you just have to understand them. So as in the trends, first of all, the ionization energy and the atomic size. So the atomic size, by the size, we mean radii, the radius. Okay, the radius that from the diameter, half of diameter is radius. So radius. So remember that the radius, the more the nucleus gets protons, the bigger the nucleus gets. The bigger the nucleus gets, what's happened? This nucleus begins to become bigger, the nuclear pull increases. So what happens to the electrons? Electrons have a very small size. These electrons get condensed. These electrons get like pulled by the nucleus with a greater force. So what happens? These nucleus, when it pulls them, to the electrons with a greater force, all the electrons, even though they are more electrons and they are in the more energy levels, yet the nuclear pull is stronger because of the atomic number, because of the number of protons, and the electron cloud condenses. So that is the deal with the atomic size. Atomic size is about condensing of the electron cloud. So it's not the number of protons, it's not the number of electrons or the number of protons. It's not about that. It's about the nuclear, the radius size, the radial size, which is condensing of the electrons in the outermost shell. So as you see now, that only happens. The electrons, the atom, in the same row means same energy level. This condensation of this will only work then, condensing of the electron clouds. But if the nuclear, the energy pull, the energy levels increase, then it doesn't work. Okay, so look at this. In this energy levels here, in this case, what is happening? In the same, I don't have the color, but if you look at the rows, the rows are the periods. These represent the energy level. So all the elements that are in the second, let's just focus on the second row will only have, fine, it will have 2s and 2p, but only one energy level. That is the name of that energy level is 2. The shell is 2. So it can have S and P, which is fine, but it's if the nuclear pull is going to be bigger on all the atoms that are in the same energy level as you go from left to right in the periodic table. So when you increase, when the size, in other words, these atoms this side in the same energy level, if the atoms have the same energy level, whether it's 2 energy levels, 1 energy level, or 3 energy levels, or 4 energy levels, whatever, as far as they are in the same energy level, the nuclear pull is more, so the size decreases. So here the atoms on the right-hand side, top right side, these in the same energy level will have a smaller size than the atoms on the left-hand side. Right? So this is a trend that the atomic size decreases you can see that you can move in the periodic table either from left to right or from right to left. It doesn't matter which side you move. Just keep this in mind that the size is small here on the right hand side and the size is big on the left hand side. Okay, that's one piece. Next is the top to bottom. When you go top to bottom, what you're increasing? You're basically increasing the energy level. So in first row, they have only one energy level. Second row, two energy levels. Third row, 3 energy levels. Fourth row, 4 energy levels. Fifth row, 5 energy levels. Sixth row, 6 energy levels, and so forth. So as the energy levels are increasing, obviously now the nucleus is unable to see the electrons that much because of the shielding effect, because of the blocking. The electrons that are close to the nucleus, they block the view of the nucleus. They block the view of the electrons that are further away. So the nuclear pull decreases. So as a result, the electron cloud, it expands. So the electron cloud is more contracted here on the top side, and the electron cloud is more expanded in all this bottom side, big, very big sizes. Okay. So that's one thing with the atomic size. Okay. Now let's look at these examples. So now so once again, I'm going to just put here top to bottom, and you can put anyways this side. So this is increasing. So the size, the radial size increases when we move from right to left. Okay, from right to left. Or the atomic size decreases when we move from left to right. That's one thing. Now here is the top to bottom. So top to bottom, going top down. So going top down, the size is increasing. Okay, so keep that trend in one place. Now here we see calcium and bromine. So let's here look at calcium. Look at calcium. Calcium is here. Okay, and bromine. Now calcium and bromine are in the same, you see this? Hold on. Sorry. Okay, so calcium is in the 4th energy level. If you see, calcium is in the 4th energy level, and bromine also is in the 4th energy level. So same energy level. If they are in the same energy level, what is happening? The size is going to decrease from left to right. As you move from left to right, the size decreases. So here we have the bromine will have a smaller size. Bromine is smaller in size than calcium, although bromine has more protons and more electrons. But when we talk about the atomic radii, we talk about the electron cloud. Electrons, these are clouds actually. Electrons are clouds. They exist as waves and particles. So electron cloud condenses. Okay, so that's one trend. And then similarly, now on the other hand, just so you know, diagonally, when you move, diagonally also, the size is going to increase when you move diagonally in a periodic table, diagonal. So keep this in mind that the energy levels are increasing. So even diagonally, if the more the energy level, if you were to compare, let us say compare sodium and potassium, which one is bigger? Sodium and potassium, right? Both of them in the S block, sodium and potassium. Sodium is smaller because it has only 3 energy levels. Potassium is bigger because it's got 4 energy levels. So that's one piece. Next is, let's look at sodium and strontium. Sodium versus strontium. So sodium is in a different column. Strontium is in a different column. Doesn't matter. But sodium has less energy level. Strontium has more energy level. Strontium is bigger in size than sodium. Okay. So that's one thing. Next is the ionization energy. What is ionization energy? Energy needed to, now the way they explain in the book, sometimes it's too technical. So energy needed to remove electrons from the outer shell. Okay, from the outer shell or the outer energy level. Same thing. So the energy, so it is the amount of energy you give from your side. You have to heat, you have to do something to remove that energy. So what you're doing here is the ionization energy, which one has a lower ionization energy. So once again, there is a trend. So keep this in mind that the electrons have the ionization energy. So this is the trend. Every atom has the aspiration to look like the nearest noble gas, which is in the last shell, like the eighth column. Okay, so here we have the last column, I mean, the 18th, or 8A. So here, this is the noble gas. Every atom wants to have the noble gas configuration. Every atom, their aspiration is to look like the nearest noble gas. Okay, so noble gases are in the purple ones shown here. Okay, so it's not letting me, but anyways, so this is the reason why they give or take electrons. So the metals will all give electrons so that they can look like the nearest noble gas, which is neon, argon, krypton, xenon. It depends where they are, or even helium, where they are in the periodic table. And then the non-metals are very close to the noble gases, right? So they will accept electrons so that and quickly get the electronic configuration of the noble gases. So here we have the ionization energy of carbon and fluorine. So fluorine is very close to the noble gas. Let's see this again, fluorine. So we are looking at carbon and fluorine. So look at carbon and look at fluorine. So both of them are in the same energy level, same shell. They have the same energy level. But fluorine, it has 9 protons. Carbon has 6 protons. So more the protons in the same energy level, the nuclear pull is strong, right? So fluorine will just grab one electron from wherever it can to look like neon, right? So it's very easy for fluorine to get that. So fluorine gets it, and so fluorine will have like very strong electron affinity, right? Now, will fluorine easily let go of the electrons? No. So its ionization energy is very high. It's very difficult to remove the electrons from the outermost energy level of fluorine because it's so close to the noble gases. Its energy, nuclear pull is very strong. Okay, so now we have, so that's way, which one will have a lower ionization energy? Fluorine has a fluorine, the energy level of fluorine is higher. Carbon will have a lower. Okay, very difficult to remove electrons from fluorine. So that is why the ionization energy is going to be high. So keep this trend in handy. Again, the trend is already given here, increasing ionization energy. So you see all these noble gases are in the 8th A, and the ones that are close, like 7A, 6A, 5A, they're so close to the noble gases, it's very difficult to remove electrons from their outer shell. But the energy levels, as the energy levels increase, then yeah, it's, then the nuclear pull goes down, and the nuclear pull goes down, what happens? Then it's easy to remove the electrons. So so this is how it's increasing. So we see that the ionization energy increases. So ionization energy increases going from left to right. And as you move up in the same column, so ionization energy is also going to increase from top down, top to bottom. Now, here's the thing. This guy will have the lowest ionization energy, the one over here. Lowest ionization energy. So low, cesium has such a low ionization. It's very easy, to remove the electrons out of cesium. Cesium pretty much melts. If you put cesium on your hand, it will melt. Okay, so you can do these comparisons. Next is the electron affinity. Electron affinity is the love for electrons. Okay, love. Okay, Okay, love for electrons. So what is the deal? Excuse me, love for electrons. So same thing, ionization energy. So same thing, electron affinity and ionization energy, they match. So as you move from left to right in the periodic table, the electron affinity increases. So all the non-metals, very difficult for them to remove. Like they love electrons, so they'll just take it from everywhere. That is why they're reactive also. Okay, and then here it is also increasing. So these guys, the ones at the bottom, they don't love electrons. They easily give away. So because the shells are increasing, the energy levels are increasing. So the electron affinity increases when you move from when you move from bottom to top. So here, I'm going to put this here, electron affinity decreases when you move from top to bottom, but it increases when you move from bottom to top. So keep that in mind, okay? So that's the thing. So here, what was the question? I don't remember, I don't forgot. Oh, arsenic and bromine. Okay, here is bromine and arsenic. So arsenic is given and bromine is given. So which one will have a higher electron affinity? Bromine, according to that trend. Okay, so bromine has a higher electron affinity than arsenic. Arsenic has comparatively low in the same period. Okay, so that finishes chapter 9. I mean, there are several things that are not covered in the exercise problems, like there should have been some questions relating to the condensed and the ground state electronic configuration and the excited state configuration and some Lewis structures, but they were not there. But I tried to cover all those things. So I hope this was helpful, and please make sure that you make a note of all these important things that we discussed. All right. Thank you. Take care. Bye-bye.